Ready to go for another exciting afternoon of more unbelievable talks today? I hope you are, because the next one's going to be great. We have the CTO of Meta Materials coming up next, the other Meta, the first one of the original Metas, Jonathan Waldern. He's going to be talking about integrating application-specific functional films into AR prescription lenses. As a glasses wearer myself, I can't wait for the day I don't have to be wearing something else on top of my glasses and fitting it inside a headset. So I'm really looking forward to the talk. So everybody give a warm welcome to Jonathan Waldern.
Great, thanks so much. Good afternoon. So yeah, my founder asked me to remind everybody we were the original Meta, but importantly, in AWE 2021, we're the only ones exhibiting. So Meta provides a broad portfolio of technology that is quite disparate in certain cases, and I'm going to run through that. I've tried to make a slide deck that's quite comprehensive and lists a lot of detail so I can annotate around that for those that may be interested in certain areas. And we basically come from a 15-year experience set in developing metamaterial science, holographic and diffractive optics, electromagnetic technologies that we use in all kinds of applications, including 5G, which I'll come on to, laser technologies, digital imaging, and indeed, in our medical unit, biosensors. So it's quite a broad spectrum in that regard. And we design materials that basically do not exist ordinarily. And these functional materials go beyond natural materials. And it's very exciting because they exhibit completely new and unique properties. And it's those properties that we're really looking to harness for augmented reality and very tightly integrate into prescription lenses. So these complex structures are patterned in metals and plastics, and they perform a special function, such as, for instance, you could have one of our metal meshes that causes the lens to heat up, eliminating fog. We have that on our stand exhibited. And in that case, you're very concerned about very high transparency. And as I come on to describe, we can achieve up to 99% transparency with that particular capability. Our company is international, rather unusually for a relatively small company. I say small, we actually listed on NASDAQ a few months ago. And we have operations with our HQ in Halifax, in Canada, where we're building a substantial new production facility for these lenses to propagate and inspire the market with regard to early batch quantities, and then through our machines, which I'll come on to describe, replicate that and build capacity internationally. We have a major facility here in Pleasanton, which concentrates on our rolling mask lithography. And this is a roll-to-roll production line. So many of the materials we're describing here are not materials you ordinarily are going to have in the laboratory, very refined silicon wafers, et cetera, very expensive meta lenses and things like that. These are roll-to-roll. And that's what really distinguishes us in terms of our heritage and ability over the years to develop these properties and lithography and other holographic techniques to become a roll-to-roll process with real opportunity to collapse the cost point for these advanced integrated materials into these applications like augmented reality. So we have many applications I described earlier in consumer electronics. 5G communications is a huge area for us right now. Health and wellness, aerospace, automotive. So we really are, quite multidisciplinary in that regard. And our vision is to have a development platform that can obviously be applied here to augmented reality. And so we're here today for the first time launching our platform, which we call ARfusion, which fundamentally is a platform bringing this functionality together and encapsulate it into a prescription lens itself. Our goal is to make AR glasses very comfortable. They've got to be all-day wearable. They have to have requisite efficiency and quality that everybody accepts needs to be very much akin to ordinary eyeglasses. And we think it's only at the base materials level that you're able to achieve that kind of integrated functionality and serve the market requirements in augmented reality, hence our approach in that respect. The key challenges in AR, as I just mentioned, are really to have that prescription capability, but address all these other, extremely important tasks. And eyeglow is unacceptable. You can't look at somebody that looks like some kind of robot. Battery life, as I mentioned, resolution for wide field of view, bandwidth of communication, so interactivity is very natural and very obvious. And so in that regard, there are a multitude of very substantial challenges that the AR industry faces in delivering that sharp, uniform image within the context of overlaying the physical world. Obviously, the glasses have got to be easy to wear, very lightweight, and really a laundry list where the lens and functional components must also be mass manufacturable. They must be reasonable consumer cost point. And that's the delta with metamaterials, is that we have this roll-to-roll capability that delivers that. So most, if not all, of the smart features can be delivered by metasurfaces. We can add eye trackers. We can add antennas. We have examples of these antennas that we've structured on our stand. Please go along and take a look. Antifogging, as I mentioned earlier. And so in that context, a holographic display can be formed using our, we have a key strategic relationship we call Vestro, a supplier of holographic film, and we record the holographic capability into that film and embed that in the lens for those displays. So in that regard, also, we can include things like electrochromic films. Why do you need an electrochromic film? Because obviously, when you move from an inside warehouse to an outside situation with streaming sunlight, you're going to have a huge amount of requirement for nits to the eye. 3,500, 4,000 nits to the eye. Guess what? That's a lot of power. That's a lot of bulk in terms of the imaging and display system. Why not simply dynamically dim the outside world using electrochromic films? You can see an example of this on our stand. So we think that the future integrated lens for AR glasses are going to have need of these features to cut down the bulk in all the rest of the situation, the rest of the glasses in terms of reducing the overall bulk of the system itself and complying with the all-day wearability that I described. Now, these fusion lenses, that we cast, what we do is we use up to 2,000 different mold sets. And we built this automated machine using roboticized stations which can select these mold sets. Once we have a mold, which is a two-part mold, much like an injection mold, they come together and seal, and then we inject monomers inside, acrylate monomers, inside of that mold to form the lens. We then UV cure that to create the lens, and then after that, there's a minor finishing as we separate out the molds. What we end up with is a very simple, straightforward process that can be largely automated, producing lenses that we can then further embed within those molds various types of optical functionality and electro-optical functionality as we build that platform out. So, for example, we can put the embedded filters into that mold before they come together, and we inject the fluid with regard to that. So the dimming layers go in as such, and so these layers really provide an integrated capability within the actual lens itself. Our cast lenses are fundamentally very high optical quality. I've put a few of the key features. And our processes meet very tight tolerances, we find. It doesn't require any high temperature curing. In fact, most of the curing could be done under 100 degrees C, which, as I'll come on to explain, allows us to use many different materials in that process. Here, for example, is a holographic film that we've embedded into the lens. This film has to be precisely aligned. When you wear these glasses and measure the transparency of this lens, what you see here is very little loss. It's almost invisible to the eye in terms of that film being embedded into that lens. Holographic optics like that are smaller, lighter, they're cheaper, and they embed integrated optical functionality that is impossible without a whole set of other lenses. So these are some of the advantages of using advanced holographic optics as we do. In this example, for example, we have embedded liquid crystal technology. Why do you need liquid crystal technology in the lens? Well, perhaps you want to make a dynamic lens for accommodation. Perhaps you want to do dimming, as I'll come on to, either through liquid crystal or through electrochromic. But what you see here is that the material survives our process because it's inherently a UV initiated process. We don't need high heat, and therefore the material sets can survive. Alignment's critical. You've got to put in the film inside the lens so it's precisely aligned, for instance, with an eye-tracked scanning projector. Or, for example, if you have an eye tracker, like in this example, where we've embedded an eye tracker into the actual lens, and of course the associated PET-based electrical connections to that device have to be maintained. They have to be precisely aligned. We figured out the technologies necessary to be able to do that, and the casting of these electronic devices is not thwarted by these intricate electrical connectivities around the rim of the lens. And finally, even for very high quality polarized films, like in a pair of Cartier sunglasses, we can embed that film and produce a commercial grade, in this case, sunglass-based ophthalmic product with the prescription lens in every case embedded in that platform. Of course, we're working on and working towards embedding two-axis, three-axis pupil expansion, or three elements to create the two-axis pupil expansion, I should say, into the actual waveguide. And we're working hard on being able to do that, but do it using volume holographic recordation techniques with our associated partnership with Bayer, using the Covestro films that we embed in the actual part itself. And with that, we've created what we call a one-stop shop. So this is the ability, alongside Covestro, for any customer to come to us with their program and for us to work deeply and well-connected with them in delivering that for the customer, so that we're the one-stop shop for that customer to deliver the resultant product. In terms of waveguides then, we can pretty much accommodate any waveguide out there. Of course, we're moving towards curved solutions for displays. We think that's very important going forward. But right now, of the major waveguide vendors, we can incorporate those into the lens itself and see that as a near-term opportunity for everybody. So embedded waveguides in there. Just briefly coming on to our electromagnetic, in this case, electronic metal mesh technologies, which we call NANOWEB. This is produced using, as I mentioned earlier, our rolling mask lithography. It's a very low-cost process for generating nanoscale metal meshes. And why are these metal meshes important? Well, it so happens that by patterning that metal mesh at nanoscale, which is totally invisible, we're able to create better methods of delivering utility such that, for example, we can switch liquid crystal from one layer versus two. We can switch electrochromic materials from one layer versus two. Why is that important? Because you're cutting down complexity in cost in the manufacturing process using that. Only NANOWEB with these metal meshes that we make can deliver that kind of capability. There's a little illustration down below of what this mesh looks like. So the mesh itself are highly conductive wires made in a mesh form that are also quite ductile. I'll come on to why that's important. It exhibits very low resistance. Try taking an ITO and getting down to 1 ohm per square. Virtually impossible unless it's a very thick film. Then try bending that ITO over a lens and expecting it to survive. Impossible. NANOWEB will conform and bend in the shape of that lens, which is very important because it now means that we have a way of embedding highly functional electro-optical drives into the lens itself using this advantage. And because it's roll-to-roll, it's extremely low cost, literally cents in delivered form for these types of devices. And that makes a big difference. You don't have to go to a coating process or go through all the rigmarole doing that with traditional vapor deposition for ITO in that respect. So why do you want to do this? I mentioned earlier about antifogging. This is very important. If you're somebody that has to work, say, in a chemistry lab wearing goggles or glasses all day, you're having a mask and it's fogging up all the time, it's a blessed nuisance. Just antifogging a pair of prescription glasses is a very useful app to have. And because our voltage, our resistance is so low in the NANOWEB, we can have very long product life in terms of battery life for those devices. They can also be timed to react to breathing, etc. In addition to that, I mentioned earlier, we can embed antennas. Now, why on earth would you want to put an antenna in a pair of glasses? Well, it's actually a very large and very useful surface. Given that this antenna would be completely invisible, we make 5G antennas that could be very effective in terms of signal reception and could enable, say, direct transmission to the glasses, thus offloading a lot of the compute power and other wireless technologies needed. So there's opportunities with antennas both in terms of transmission and reception, and we are active in making highly efficient antenna designs, which once again can be printed inside the lens itself. Just a little bit about our automated lens casting system, or ALC. Here's a little process summary, but basically with this process, we have the cavity with the 2 glass molds to remind you. The fluid comes up, we cure it, which is UV curable acrylic monomer. The foil, the preformed foil, etc., is embedded within, and then afterwards the actual molds are opened and out pops the lens. If you want to see this machine, which is actually a little bit of poetry in motion if you watch it, please come to our stand booth. You'll see the big Meta sign over top, and take a look at the video. It shows all the roboticized process steps as we go through that. And we're making great progress with this ACL process because the ALC process, I guess within our last generation 4, moving to this generation 5, has shown substantial improvements in performance. Of course, we're trying to get the cost of the lens piece part down. We estimate $10 per lens at the moment with the functionalization. And trying to drive that down is a function, obviously, of speed and throughput. And in addition to that, ensuring that we can improve on the various functional steps within the machine tool. So we think we've got a terrific roadmap to improve that performance and drive that cost down, but deliver the functionality. You can see the tool here, which has the various steps, including the automated selection of the mold pairs, the input of the monomer into the machine tool, the photo curing, and the mold opening. But it's much easier to see the video in that respect, which is on our stand. These are the various pieces in the process steps as we go through. And you can also see again, as a giveaway from this presentation, all the relative specifications which may be pertinent to some of your interest in this particular process. So the current lens prescription design space and the material properties are all listed here. And in addition to that, it's worth saying that the process itself can be tuned to customer requirements. We do have customers that want extraordinarily large throughput and volume, and largely at the moment, it's really replicating the nodes so that we can increase the capacity through doing that. And then finally, this process delivers high levels of efficiency, a repeatable quality and at volume. It's a mature process. It's not brand new. It's certainly not out of the lab. This process has been going the last couple of years, but we've really added to that process the whole AR capability now, which we're launching at the show today, and please come to our stand. And clearly, you want to compare this process that we have, our ARfusion, with conventional ophthalmic lenses. What are you guys doing that's any different from the way my lenses are made? Well, there's two key steps right there in terms of there's no cleaning, there's no polishing, there's no post-coating. So there are various steps that we eliminate through the fact that we're injection molding these lenses and providing them a very high quality as they come out of the mold. And to boot, environmental advantages exist in terms of there's no water demands, there's no material wastage in the actual process. So we also think with the high-speed UV hardening, power consumption is fairly minimal. So this is an environmental friendly process as well, which is very important to Meta as a corporation. Finally, these are a list of the key unique selling points that we think condenses the differentiation between our platform and others, and in that respect helps to distill folks' inquiries and where we really are different. So again, Meta provides a broad range of portfolio technologies combining outstanding knowledge from the 15 years, as I mentioned earlier, of experience, our metamaterial science, fundamental capabilities, our holographic and diffractive electromagnetic technologies, combined with this roll-to-roll capability. So this is not a lab-scale experiment any longer. This is real deployment for high-capacity delivery of quantity. And please, come and see us on the booth. There's, as I say, videos, and several of our scientists are in here from around the world to answer any questions that you may have. And generally, we're very enthusiastic about the whole metaverse. We're the original Meta, and AR in general. But we do think that a lot of attention to detail needs to be applied at the fundamental materials and integration steps to really get to the quality that we need in glasses. Otherwise, it would have all been done by now. Thank you all very much. And if there's any questions, please go ahead.
Yeah, thank you, Dr. Waldern. That was great. So yeah, if there's any questions, please come up. We've got 2 mics up here in front, and we'll take questions. Yeah, so anyone feel free to come up. While people come up, oh, there we go. We got a first customer. All right, right here.
Hi, I just wanted to ask, I missed the part about how many functions you can layer onto a pair of glass or a pair of lenses.
Well, it really depends on the requirements with respect to both the exact specification, what's required. Is the film thick? Is it thin? Is it what level of dimming, what level of clearing, et cetera, et cetera. But the functions that I described, which include things like heating, things like electrochromic, things like integrated holographic display combiners or a reflective film, these can all be fabricated on substrates. We use willow glass, for example, which can go down to 100 micron per layer. So if you look at the laminate that might exist, say, at 100 microns, and integrate that across, say, those 3 or 4 functions, plus that we can only use 1 layer of electrical conductivity, then you soon come to the equation that you could produce an integrated lens like that in less than a millimeter.
But only one could be electronic?
Pardon?
Only one function can be
No,
electronic?
that's multiple layers electronic.
Okay. So up to 4 functions?
Um,
Maybe 5?
Yeah, I would say in that description that I just described, 4 functions is a figure of merit. Yeah, yeah.
Thank you.
You're welcome.
Any other questions? Feel free to come up. So how long until my glasses are AR glasses?
Well, as you might imagine, we've gotten a lot of interest with this platform. Seeing is believing, and we can clearly demonstrate it. And so in that regard, the sort of timeframes that we're being alerted to that we need to deliver is roughly around 2 years to broad deployment in terms of prototypes going out. Quite how long the application and development community take to enable this is another question, but around 2 years, I think, is a figure of merit. Yeah.
Okay, awesome. And any other question? Oh, you have another question coming up. Perfect. Time for one more.
Yes, sir.
Hi, Jonathan.
Hi.
So as you know, a near-eye display system is a very tightly integrated system with a lot of trade-offs. So how do you handle the image source or the so-called display? Are you developing the whole subsystem, or?
That's a great question. We're largely display agnostic. AR is getting to a point now where to re-engineer display solutions from scratch and try and be competitive is just, in our view, a little bit silly. There's plenty of very impressive MEM scanning, micro-LED, of course. We're very much looking to that future, especially with our meta lenses in front of the micro-LED to compress and enable and contribute to that compression and integration. So I guess to a certain extent, we're not really too focused on the image generator, as I call it, or indeed on the waveguide optic at the moment, but rather the integration of everything into the lens. That's where we think we can make a good contribution in terms of our expertise and our capabilities in getting product to market as quickly as possible.
Okay. Because as you know, the emission characteristics are different for different sources. And so question, I guess, is it sounds like you're almost doing custom projects. You work with somebody in a vertically integrated design versus a off-the-shelf kind of component that someone can plug in.
That's right. Invariably, there's quite a deal of customization to work in it. But I guess our disposition is really to create an ecosystem around it to get to the product, rather than try and do the desperate parts ourselves individually, if that was the question.
Okay, good.
Yeah.
I'll catch up with you later. Thanks,
Sure.
John.
Thank you.
All right. Thank you. I think it's all the time we have. Thank you, Dr. Waldern. And yeah, thanks very much.
Yeah, thank you.
All right.